Started. Welcome everyone to the next iteration of tinyML Talks. Our sponsors are Edge Impulse. They provide a developer platform to take machine learning from design to deployment at scale. Visit edgeimpulse.com for a free trial. I'd like to also make an announcement about an upcoming event. Joint webinar with the IEEE Solid State Circuit Society and tinyML, the intersection of Solid State Circuit Society and AI, a tale of two journeys. Professor Boris Merman and Professor Vivian Z will be speaking on Tuesday, May 26th, 8 a.m. Pacific time. Also, our next tinyML talks on Thursday, May 28th will be by Laszlo Kindrat and Michelle Magno, two great talks coming up. Again, same time, 8 a.m. Pacific on May 28th. Please contact talks@tinyml.org if you're interested in presenting in an upcoming tinyML talk. We have Jamie Campbell from Synopsys. Jamie Campbell is a software engineering manager at Synopsys, leading teams responsible for the development of machine learning inference library for Synopsys ARC processors, and the creation of compelling demos and reference applications for the Synopsys embedded vision processors. Prior to focusing on machine learning, Jamie has worked in various capacities as an embedded software specialist, including R&D engineer, field applications engineer, and corporate applications engineer at Precise Software Technologies, ARC International, BioRidge Logic, and now Synopsys. Jamie holds a Bachelor of Science in Electrical Engineering from the University of Calgary in Canada.
Okay, thanks, Ravi. Good morning, everyone, and welcome. So for my talk today, divided it into about 4 different sections. I'll just start off with a brief intro, and then we'll look at ways that in a deeply embedded environment, we can improve inference efficiency. Then I'll bring in the TensorFlow Lite for microcontrollers, mentioned in the title, and explain how that can help ease your programmability. And then finally, I'll finish off the talk with a couple of demos so we can see everything working live. So let's jump in. Just quick introduction here in terms of the application domains that we typically consider always on AIoT. These will be some sort of sensing applications, so monitoring potentially human activity, heart rate, those sorts of things. Applications which are always listening for keywords to wake up, or other applications which are always watching, detecting the presence of a person, a face, or those sorts of things. So the processing requirements vary. A few factors there, of course, the complexity of the model, the type of input, your frame rate, and those sorts of things. And of course, on the vision side, something that's always watching tends to consume, be more demanding in terms of processing than the others. So even when users are more interested these days in vision-based systems for applications like gaze detection, to turn on your TV when you walk into the room and look at it, to wake up your device when you look at it, etc. They still have pretty high expectations about how they want to interact with these systems, and that they want them to be responsive, to wake up when you interact with them. But of course, for those that are battery powered, they're also demanding long battery life. So the question is, what can we do to kind of address these two needs from our users? So really, to kind of look at what we need to achieve, we have to build systems that are always sensing, continuously monitoring, that have real-time performance, and also offer low power consumption. So I kind of call this the ML developers or ML edge developers challenge. So there's 3 pillars there. Systems have to be high performance, yet low power, and also easy to program. So the programmability is really for you as a developer. You have time to market constraints. You want to make sure that You can get your systems developed quickly. So we need to find ways to make your life easier as a developer. So we'll cover these three things in this talk today. So how do we achieve our goals? Well, clearly we need an efficient processor coupled with a rich software environment. So let's talk about the first pillar, which is the performance side of things. So if we look at a typical workload for an NN application, this really consists of a lot of convolution operations. And convolutions themselves are really made up of low-level dot product operations. So what we're doing here in the case of a vision-based application is we're taking a frame of input data, as well as the training weights from our graph. We're multiplying individual pieces of those together, accumulating the results, and storing them as an output. So this multiply accumulate operation is something that's typically handled by a DSP. So it should be familiar as a DSP operation. But if you think about the whole system, a typical IoT device also has control code to execute. So it's driving a sensor, for example. It's probably communicating with the outside world at some point. So really what we need is an embedded processor that can combine both RISC and DSP capabilities. So looking a little bit more at the type of operations that we have to do, we've already talked about the first one, multiply accumulates. But because we're working across arrays of data, we need efficient ways of looping through our elements as we process it. And then thirdly, probably the most important, is how we can effectively deal with all of the data that we need to process. And especially in the cases of images where resolutions are getting higher, we need to be able to efficiently read in that data, potentially unpack it, sign extend it, and then after processing it, write the outputs. So how can we focus on those three operations and handle them efficiently? So by way of example, I'd like to introduce the ARC EM9D processor from Synopsys. So this is a RISC processor with a three-stage pipeline that has DSP ISA extensions as well. And if we look at the problem we're trying to solve today, there's three key features of the ARC EM that can help us here. So the first is multiply accumulate instructions that can operate in vector fashion. So that means that they can do more than one multiply accumulate per cycle. There's also a hardware capability called zero overhead loops, which allows us to eliminate loop management instructions in our code. And finally, the most important is the XY memory, which is a type of local single cycle memory that exists within the processor. And that works together with a hardware unit called address generation units, or AGUs. And those two capabilities working together are what's going to allow us to access those weights and feature map data in an implicit manner. So there's basically instruction level parallelism built in to the processor. And we're going to be able to do a lot of that data access overhead at the same time as we actually do the calculations. So I think the best way to kind of understand the benefit of this is to kind of dive under the hood a little bit and look at some assembly that could be generated by our compiler if we tried to implement one of these multiply or dot product operations. So the first snippet here is the original, let's call this unoptimized code. So if we look at this, we have first instruction is initializing a register with a loop count. Then we go into our loop, and the first thing we need to do is bring our data in to registers for processing. So we've got a pointer to our weights, a pointer to our feature map. We load those in. Then we actually implement our multiply accumulate instruction and store the results into the accumulator. Next step is to increment each of our address pointers. Then we decrement the loop counter. And if that loop counter is still non-zero, we have a branch instruction back to the top of the loop. So our first optimization is to apply a vectorized multiply accumulate instruction. So this effectively allows us to reduce our loop count by half. And we still have the loop, but we don't need to go through it as many times. The third optimization is to bring in the zero overhead loop capability. So this allows us to reduce the number of instructions inside our loop. So what we've changed here is we are now using this special register called the loop count to keep track of the number of loop iterations we want to do. And we use the LP instruction to, outside of the loop, to tell the hardware where the end of the loop is. Then as we execute the loop, it will automatically, once that end instruction is reached, it will automatically decrement the loop count. And if it's non-zero, the hardware will automatically change the program counter back to the top of the loop. So as you can see, that's allowed us to remove 2 instructions from our loop body. So already our loop is getting shorter. We have less work to do. Now let's look at the third optimization, which is probably the most important in terms of its effectiveness in improving our efficiency. So here we're going to bring in the XY and the AGUs. So really the AGUs, what they allow you to do is implicitly access your data. So they are special registers, or their AGUs are accessed through special registers that have side effects. Outside of my loop, I need to first program the AGUs to do things like point to the start of my data. I also specify how much I want to increment the AGUs every time they're accessed. I can specify a wrapping. I can also specify if any unpacking is needed, sign extension, etc. So that's all done outside of the loop as part of the setup through a couple of instructions. Then inside my loop, which you can see now has degenerated to a single instruction, instead of directly accessing those pointer registers, I'm accessing the data through these special AGU registers. So simply by using those AGU registers in my instruction, I'm actually reading data in, incrementing pointers, doing any modifications to the data, like unpacking it, etc., all just by implicitly reading that register. So if we look at what we're doing in our loop, we're actually doing loading, unpacking, sign extending, our dual MAC, storing the results to the accumulator, and updating the pointers all in a single cycle. So this is really a way of having one instruction do many things through instruction level parallelism and vastly reducing the number of cycles we have to spend in our loop for these dot product operations. So why is that important? Well, I think it was pretty obvious that we saw the performance increase. So clearly, if you have less instructions to execute, you're going to get your results quicker. But this also touches our second pillar of the ML Edge Developers Challenge, which is power. If I have less instructions in my code, my loop got smaller. My code is smaller, which means less memory. So of course, I don't have to burn as much power keeping memories alive because they're smaller. I can also get the same work done in fewer instructions. So that means I can meet my deadlines, but I can run my CPU at a lower clock speed, or I can spend more time sleeping, both of which will serve to reduce power. Now, I could also argue that this will improve the responsiveness or reduce the latency that our users see. simply because we're executing faster. And finally, this can also help with accuracy as well. If I have efficient ML routines, I can make the graphs that I want to execute. I can have more layers in them. They can be more complex, which presumably will give me more accurate results for my inference. So that really touches performance and power pillars. Before we move on to the programmability, just wanted to see, Ravi, if there was any questions.
Yeah, there's actually a few questions that are coming up. One of the things somebody asked was the EM9D that you presented. Is that available in the market right now?
Yes, good question. So just to clarify, Synopsys, we actually sell processor IP. So typically our customers are people who would build chips and then would sell those chips to the market. So a bit later in the presentation, I'm going to introduce one of our customers, Himax Technologies, who's actually built a chip based on the EM9D that will be available soon.
Okay, just to follow up on that, I was going to ask about the size of the networks, like in terms of the weight memory that can fit on the fit in the memory that you talked about, the XY memory. Mm-hmm. Would that also be depend on the kind of instantiation, like the how they manufacture it?
That's right. So the core is customizable. So you actually get a tool, if you license the RTL, you get a tool that allows you to configure all things about the processor, including the sizes of the XY memory. So you can look at your application and how big you need to make the XY. And also later in the presentation, I'll touch on a feature in our software stack that can help you most efficiently access that XY as well.
Excellent. That's all I have for now. Please.
Okay, great. Okay, so let's continue on then. We're looking at our Edge Developers Challenge, and we have this third pillar about programmability. So again, your time to market constraints, you want to get your product out the door quickly, and how can we facilitate that? So we've seen that efficient, optimized code is important, but presumably you as an application developer don't really want to spend time writing this optimized code yourself. Why not let the experts do that? So you should look for vendors who supply libraries, software libraries of ML routines, which can facilitate your programming tasks, and you can focus on your own differentiators. So just by way of introduction, I'd like to show you the Embark Machine Learning Inference, or we call it the MLI library. So this is a library of ML kernels, which is really focused on, today is focused on low-end IoT type of applications. It supports both CNN and RNN kernels. And of course, the kernel implementations are optimized for the EM processor, similar to in some of the ways like I explained a few minutes ago. This is available as an open source distribution via our website, embark.org. So you can check it out today. All right, so continuing on with the programmability, yes, it's important to have a library of kernels, but NN graph development is more than just calling a bunch of kernel APIs in sequence. So if you look at the development process, the first thing you need to do is actually design your graph and train it, which typically happens on a development workstation. And then to move that over to an embedded environment, you have this mapping process. So that involves quantizing the data from floating point into fixed point. And then in a constrained embedded environment, you need to think about things like memory layout and how everything will fit onto your target. And that mapping process can actually be quite a bit of work. And then once that's done, you finally get to run it on your embedded environment. But what I would suggest here is that you really need to consider using some sort of framework that can help you with the design and the mapping process. So that's where we introduce TensorFlow Lite for microcontrollers, which is from Google. So this is a port of their TensorFlow Lite stack, but it's designed to run ML inference on microcontrollers with extremely limited memory. The benefit here, though, is that all of the same tools that you're familiar with in TensorFlow can still be used for the graph creation and training. And then when it's time to migrate to the deeply embedded side, there's an established conversion flow that you can use. So you sort of get the best of both worlds by using such a framework. Okay, so if we want to put this all together, I've shown you a bunch of components so far. So I want to give you a view of how you build a system using all of these pieces. So you would have some application, AIoT application. You will have developed and trained a graph, converted it to the TFLM, TensorFlow Lite for microcontrollers format. And you will make a call from your code to the TFLM interpreter. So it will read each layer of your graph and execute it. Now, in order to do that, there's a couple of things it can do. Out of the box, TFLM ships with a bunch of reference kernels. So these kernels can be compiled for any architecture and run on them. So we could directly run the reference kernels directly on the EM9D processor. However, to increase the performance and the efficiency, what we have added to TFLM is an ARC-specific backend. So that backend, its first task is to actually map the TFLM kernels to the kernels which exist inside our optimized MLI library that I've just introduced, which of course run also on the EM processor. Now, the other thing that our backend can do is implements what we call layer slicing and data movement. So this kind of goes back to Ravi's question a few minutes ago about the sizing of those fast local memories on the target. As networks become more complex, your weight sizes grow, your IOs get bigger. But at the same time, you don't necessarily want to have huge local memories on your target. So there's always a balance there about sizing your memory and being able to execute your graph. Now, with these slicing and data movement APIs, we try and help you with that task by basically giving you the ability to not worry so much about how to fit all of your graph pieces into the local memory. The slicing APIs can take a pointer to a large tensor, cut it up into slices, and process the results slice by slice. So this allows you to achieve those performance benefits that I explained with the instruction level parallelism on the EM, even if your graph is larger or too large to fit in local memories. So you kind of get the best of both worlds by using the backend. Okay, so just to kind of wrap things up, I have a couple of short demos to show you. So the TFLM stack comes with a couple of examples, and one of them is called a person detect. So it's a graph which detects, takes an input 96 by 96 input image, and it detects whether there's a person in the image or no person. So you get two different outputs. So for the first demo, I'm going to run this example on the ArcEM software development platform, or the SDP board. So this is an FPGA platform that Synopsys provides. So I'll just hold it up here. It's relatively big, doesn't fit into about the size of my hand, so it doesn't really qualify as a deeply embedded thing that you would actually deploy in the field, but it's a great development system. It has a lot of different IOs and connectors for prototyping. So today I've got my board powered up, and I've also connected to the USB port to my PC. That USB is going to serve two purposes. One is for a JTAG connection. So we're going to drive the debugger. We're going to drive the board through the debugger. And there's also a COM port connected as well, so we can see the output. We're going to run the example twice, once with this dog.bmp and once with person.bmp. So here's my command prompt and then my UART port. So I'm going to invoke our debugger with the precompiled image and pass in dog.bmp, which will get downloaded over the JTAG into memory. So this is loading the code into the device, and then the output, you can see here, we're processing dog.bmp, and it does not detect a person. So it seems like it's working as we expect. The other thing I want to draw your attention to is the profiling here of the inference time. So you can see that we managed to run the TFLM person detect example with the MLI libraries on an EM processor in under 14 million cycles. This is actually quite an aggressive number compared to some of the other targets we've looked at. So we're quite pleased with the performance we're getting there. Let's try that again, and now we will pass in person.bmp instead. So we'll repeat the process, we'll load the application, read in the bitmap, and now you can see that a person is detected. So seems like person detect is executing as we want. Okay, so now let's move down into the more of a deployable, a demo based on a deployable system. So this is a platform from our customer and partner Himax, who've developed an SoC called the WE1 Plus with an RTM9D inside. And in addition to the processor, they've added a number of hardware accelerators, power efficient hardware accelerators for doing various types of detection. And their ASIC is basically targeted towards battery-powered, low-powered, smart appliances, surveillance, and that sort of thing. So the board is quite compact, 40 millimeters by 40 millimeters. It's got a PIR, passive infrared sensor on the front, a camera built in. So it's basically ready to go to run these person detect examples. So here's how the example flow looks like. So this, because of the logic, the shutdown logic in the target, it spends a lot of time sleeping. If the passive infrared is triggered, we'll wake up, the camera will do a detection, the image will be resized, we'll pass it into TFLM person detection, a light will come on if it's detected, or stay off if it's not. So you can see the timeline here where we're sleeping most of the time and we wake up and consume more power while we do the inference and go back to sleep. So they've measured power on this target. Average power consumption, if we consider about 1 frame per second, is about 2 milliwatts. So let me just briefly zoom in here quickly. You can see the board here. So it's tiny. They've just added a holder and a battery on the back. But here's the 4 millimeters by 4 centimeters by 4 centimeters. So you can turn a little bit. You can see that it's looking at me. The LED is on. If I cover it up, cover the camera up, the LED goes off. It doesn't detect a person. If I uncover it, it detects me again. So it seems like that example is working as we expect as well, but in a much smaller platform. Okay, so just to wrap things up here, just some key takeaways for you. So really what I wanted to show today was that these two objectives of both high performance and low power does seem to be achievable for ML systems. by leveraging architectures with special features like instruction level parallelism that can help you with the most efficient implementations possible. Then you can also facilitate your development by finding vendors which supply optimized ML libraries and using frameworks like TFLM. So you can give that a try today. I've got some further reading for you. The embark.org site is where you can find MLI. You can find information on Himax's chip here on the second one. And within the next day or so, we're just waiting for a few regression tests to finish on Google's side, and then you'll be able to access the ARC-specific implementation on TFLM's page. So that takes me to the end. I guess we're probably have time for a couple of questions, Ravi.
Great. Thank you. That was a very informative talk. I think these two talks really kind of complemented each other very nicely in terms of being the demand and supply side of tinyML. So yeah, one question that I had was about the 2 milliwatt number per frame per second. Could we dive into that a little bit more? Is that the end-to-end system power, including the camera and the PIR sensor power, everything together, or the processor power alone?
Yeah, I should probably defer that to Himax. I believe it's the complete system power. They measure the current on the board and they know the voltage, so they can derive the power. But maybe we could leave that on the forum, and sure. I will just check with Himax and have them answer the question to give the most accurate answer for that.
Okay, thank you. Another question that appears to be quite popular is, how does the DSP-like instructions in the Codex M4 and M7 stack up? The
DSP functionality of the EM?
Yeah, I think that's what they're asking. I was just reading verbatim the question. I think they're trying to compare like M4, M7 for like these DSP type instructions like multiply and accumulate.
Right. Okay. So yeah, I mean, some of the advantages that we offer, like I mentioned, were the ability of the XY memory and the ability to really do that instruction level parallelism, so that we can eliminate those, the overhead of loading, modifying the data through sign extension and those types of things. That's really the advantage that we offer on ARC that can really increase our performance.
Thank you. There's another question. Can Mac operation do SIMD? For example, how many 8-bit times 8-bit Macs in one instruction?
Yeah, okay, good question. So, the focus of the EM processor is not to be some super wide vector machine, because that, of course, makes the processor much bigger, much more power hungry. So we have when we say the vector Mac or the dual Mac, we can do 2 wide, 2 Macs in one cycle. And that focuses with 16-bit data. So, but we believe that through these other techniques that we've mentioned in the talk, that even though there's other systems which are wider, those systems suffer from having to do those extra kind of setup code, memory access code, which ends up degrading from the benefit you get from ultra wide calculations.
Thank you. Another question is about whether the processor architecture is available or will be available in the TVM stack. If you're familiar with TVM.
TVM, okay. We're not actively looking at that at the moment, but we are certainly open to, at least with the EM family. There's things, other projects where we are looking at TVM, but we are open in the future to looking at other frameworks. So if there's a need there, it would be something I'd be interested in hearing more about on the forum. If someone would like to contact me directly, I'd be open to discussing that more.
Great. I know we're a little bit over time, but I'll try to cover a couple of more questions. There was something about zero overhead loop and AGU instructions. Do we need intrinsic functions for these, or our compiler will generate them by itself?
Yeah, okay, so the zero overhead loop, the compiler definitely will, as long as you tell the compiler that you have that feature in your configuration of the ARC, it will leverage them. The compiler will also be able to use the AGUs. What you do need to tell the compiler is that the data that you're accessing, when you declare a variable in your code, you would prefix that to say that this variable should go into X memory, this other variable should go into Y memory, and then the compiler will generate the appropriate code to access it through the AGUs.
Thank you. Another question, is there a simulator available via Synopsys to get latency numbers for different use cases?
Yeah, so we have a couple of simulators. There's functional simulators that come with the tools, and then we also have a cycle accurate simulator that's of course much slower, but fully cycle accurate that can help you get performance numbers when you run the code.
Yep, and we'll take one last one in the interest of time. What are the hardware requirements like RAM and flash for the person, not person example that you showed?
Yeah, okay, good question. So there's, of course, two components we need to look at here. One is the size of the MLI libraries, specifically the functions that you, the kernels, the specific kernels that the person detect calls from the MLI library. And then you also have the overhead of the TensorFlow Lite for microcontrollers. So if we look at just the kernels themselves, it's just off the top of my head, I think it's in the order of like sort of 10 to 20 kbytes. I think closer towards the 10 kbytes for the kernels. And then the TensorFlow Lite, the interpreter, and all of the other things, and this is code size, by the way, around 50K for that. And I'm sorry, I don't recall the data off the top of my head, but it's in the order of tens of kbytes as well. So.
Thank you. Please do feel free to continue the conversation at tinyml.org/forums. We will update the questions that you've already posted here that we haven't been able to answer over there, and we can get our speakers to answer the questions there as well. Once again, I'd like to thank our sponsors, Edge Impulse, and if there are additional sponsorships are available, so please contact Betty at tinyml.org if you or your organization are interested in sponsoring an upcoming talk.